All right, welcome. Final day. I heard class is canceled. All right, we're gonna wrap up some 13, which is carbohydrates. Maybe we'll look at some other things too, and then we'll call it a semester, I suppose. Unless of course you have lab, then you should probably go to lab. So I imagine today. Um, I imagine. All right, we're into chapter 13 there. And that is about carbs we talked about, I think. And carbohydrates obviously are made up of, as we saw, carbons, hydrogens, and oxygens. Again, that we saw that they basically have two of the same sort of functional groups that we saw in organic chemistry. They do have the aldehyde group there at the top. They typically will have several, perhaps chirocarbons happening. And we can classify this guy as an aldo or an aldose, as it has that aldehyde group up on top. We also, again, where these intersections are also carbons. We could count up the carbons there, and we could classify it based on the number of carbons. I think I did 6 there, 2, 4, 6. So this would be something like a hexose. We also talked about the other sort of functional group that we do see as well in carbohydrates, which is really the ketone group there. And I'll just write the carbon there so we can see it. And once again, this is really our ketone group, just like we saw in organic chemistry. Our 3 carbons in a row with our double bonded oxygen there in the middle. And that's going to be a keto, or a ketose. And also, again, you could classify it, let's see either, as based on the number of carbons. Just like in organic chemistry, because of this hydrogen, it will always find itself there up on top at the end, the carbonyl group. Also, because you need those 3 carbon runs, like we talked about, that guy there will find himself usually the second sort of position in this ring or in this structure. We also talked about L and D, again, the placement of that last hydroxyl group or OH group furthest away from the carbonyl carbon, and at that furthest chirocarbon away from it. Remember, again, a chirocarbon has 4 different groups sort of attached to it. I think we finished up talking about how to put these guys into sort of cyclic structures and then take them out of cyclic structures. So if we did have just a made up little carbohydrate action here. 4. And in this particular case, if we were going to put it into a ring type structure, one thing you could do is they tell you to kind of just drop it on its side. And if you drop it over, as we talked about, everything on the right-hand side there will end up down, and everything on the left-hand side will end up upwards. And again, if you sort of do that, you'll end up with something like this. And when we do number, just like an organic, that guy's going to take the priority. So that would be carbon 1, 2, 3, 4, 5, and 6. And obviously here we would draw it like we just dropped it there. And in this situation, when we have sort of this hexose sort of guy, that's going to be that last chirocarbon pretty much from the carbon oxygen double bond. that's going to come in and pretty much attack the carbon oxygen double bond. That, as we talked about, is going to give us a choice of really sort of two types of rings that we saw. One is really a five-member ring, five-carbon ring that has the oxygen incorporated into it, and one is more of a four-carbon ring that has the oxygen incorporated into it. So when you kind of do that little arrow there, that will show you pretty much which carbons or how many carbons should be in your ring. So that's 1, 2, 3, 4, and 5. So that tells us that we really should go with this guy right here. And since we're going to go with that guy right there, I'm going to erase the other guy, I think, first. Get rid of that. What always ends up happening with this sort of 6-carbon or that N carbon that's not part of the ring is it always ends up sort of to the left of the oxygen in the ring and above it. And again, that would be sort of your orientation for carbon number 6 in this case. You then could go to the ring and sort of number counterclockwise here. Counting correctly, I suppose, would be good. And remember that it is sort of, in this case, the 5 and the second carbon that's coming together. And that's where the oxygen gets incorporated into the ring, as we talked about. What's going to essentially happen, as we mentioned, is this hydrogen will eventually kind of work its way over there to that oxygen. And that's going to make one of the OH groups that we're going to have at the end there. And that other oxygen right there is pretty much this guy that gets incorporated sort of into the ring part of it. So because of that whole incorporation at carbon number 5, in this particular case, we do skip it and we go to carbon number 4. And we can see that the OH group is down. So we would write our OH group down. We go to carbon number 3 there. Our OH group is up. So we would write it up. And carbon number 2 there, our OH group is down. Now, the last OH group is dependent on whether you're asked to draw the alpha or the beta anomer. And alpha means that the last OH group goes downward. And again, the only difference here, as we talked about, I think last time as well, is if you were going to draw the beta, you're just going to draw that last OH group there going upwards. So if you're going to do the beta, it would look something like that, I believe, in that particular case. They will tell you when you're asked to draw those type of things, to draw either the alpha or the beta. Any questions on that there? Now we saw, again, if your ring is going to sort of end up at that 4-member ring, usually what will happen is you'll have another carbon group kind of off of the ring there, especially if it's a ketone type group that is present. We also talked about that if you had a ring type structure, and as I mentioned before, this sort of OH group is coming from that H just coming up here. And again, that oxygen gets incorporated in there. If you had a ring structure like, actually, let me just draw. Yeah, we'll do this one. That's fine. And we wanted to kind of open up the ring and draw the D version of this. That D will tell us basically where to put that last OH. In this case, when we look at it, we could count the carbons, and obviously this is 6, 5, 4, 3, 2, and 1. So we know we do have 6 carbons. We also know, as we look kind of over here, there is no other carbon group kind of hanging off of it, which means we most likely have the aldehyde group there at the top. So that's how we could kind of recognize that we got this guy going on. You could lay up your 6 carbons if you like, 2, 3, 4, 5. And we know that this guy right here is going to be carbon number 6. This guy's going to be carbon 1, 2, 3, 4, and 5. At this point, we could just kind of work backwards. So like we talked about, when we drop our structure on its side, anything on the right-hand side ends up down, which means this OH on number 2 should have started probably there on the right-hand side. When we go to number 3, it's up, which means it should have been on the left-hand side. Here it's down, which means it should have been on the right-hand side. And again, the D here will tell us that our last guy should end up there on the I guess that right would be on my right-hand side. I know. I'm just making sure you're paying attention here on the last day. It's all right. It's right, left. Let's try that again. Right would be over there. There we go. And that would be left. There we go. That would be much better. Um, any questions on that there? All right, so you do need to be obviously able to draw them into a ring structure. Perhaps that might show up somewhere like next week. And maybe you need to be drawn out of a ring structure. I'm not sure if it'll show up, but one of those two might show up next week, perhaps. Just talking out loud, I suppose. All right, so we kind of went through that. And again, we'll just kind of scroll through it since we did talk about it there. And again, our beta going up, our alpha going down. As we talked about before, this does create that cyclic hemiacetal. And a reminder that the hemiacetal, right, is a carbon that has directly bound to it an OH group, that sort of oxygen carbon group, and a hydrogen. And that is sort of what we see here. We got the H, the OH, and this sort of oxygen carbon group coming that way as a result of really the carbon number 5 and number 2 coming together. And there you can see again, this hydrogen is going to kind of do a slide over move, and that's going to produce that hydroxide. And the oxygen that's left there will obviously get incorporated kind of into the ring structure as we talked about. Now, in terms of alpha D glucose and beta D glucose, these guys will kind of open up and close these type of structures. And you can see in a lot of cases, a major sort of percentage does end up being actually the beta glucose. And really, again, the only sort of difference here is, again, the location of that one, which is, again, basically carbon number 1 in each of those cases. As again, that is 6, 5, 4, 3, 2, and 1 happening there. Fructose as well will kind of do a similar type of deal. It will kind of close in. Remember here, though, it is going to be this guy that's going to always find the carbon oxygen double bond in this case. So I think as we drew last time or something similar to this last time, the result of that is you got 1 carbon, 2 carbons, 3 carbons, and 4 carbons is going to make up the ring. Hence, we go with the smaller ring there. That also leaves, which is a little bit different, both of those groups outside of the ring. We still start the same way. We put that last carbon off of the ring there, and that would be carbon 6, 5, 4, 3, 2. And now our last sort of carbon there is actually off of the ring, which is carbon number 1, which is this guy up here. In that particular case. And obviously we have our alpha fructose, which are our OHs on the bottom, and our beta, which are OHs on top. In this case, you do need to include that group there in the drawing. You can't leave it blank, right? Otherwise it implies that it's just the hydrogen on the other side. So you got to make sure that you do include that group on that one. All right. So let's try one more. Why don't you put this guy into a ring structure here for alpha? Okay, so let's take a look here. Once again, we'll just number our carbons. So we have our orientation 1, 2, 3, 4, 5, and 6. Now, if you want to redraw it on the side, you can, or again, you could just remember, like we talked about, that right is down and left there is up. So if you don't want to just redraw, you could just remember that, and that's a easy way to kind of do it as well. Here we do, and this hexo is going to have that 5 going out to the carbon oxygen double bond. That's a 1, 2, 3, 4, and 5 member ring. So we know that we should have creatively drawn ring right there. We know again that our carbon number 6 there will end up to the left of that oxygen above the ring. That is then going to give us our 5, 4, 3, 2, and 1. In this case, again, we're going to start at carbon number 4. My OH group is to the left, which means it should end up. carbon number 3 next. OH group is to the left, which means it should end up. And carbon number 2, OH group there is going to go down. And again, the last sort of OH group is going to be based on what they asked us, which in this case is alpha, and that should go up or down. Should go down, yeah. So we'll get a little bit of action like that, yeah. Any questions on that there? All right, so make sure you know how to do that, yeah. They agree. That's good. They agree. Very nice. All right. All right, let's talk about some chemical properties of these monosaccharides. Now, a lot of these guys are referred to as being reducing sugars, and these are monosaccharides with carbonyl groups that can oxidize to give the carboxylic acid. Because they're reducing sugars, they could undergo a reaction with Benedict's reagent, and it will give obviously a positive result for that. They include pretty much the monosaccharides, glucose, galactose, and fructose. Also some of the disaccharides as well. Really, the only sort of non-reducing sugar is sucrose, because it's got a different connection. We'll take a look at it in a sec on that sort of first carbon there, the alpha carbon or the beta carbon, and it cannot sort of reduce it because of that. But all other sugars pretty much can do sort of the reducing part of it. It's pretty much similar to what happens in organic chemistry, pretty much identical. Again, remember that our Benedict's reagent is kind of bluish when it starts, and that's the result of the copper being in the +2 positioning there. It's going to oxidize our carbohydrate in this case, and pretty much you could just think of it just like we did with aldehydes, right? If we oxidize an aldehyde, we get a carboxylic acid, right? And that's pretty much the same deal that happens here. Nothing else changes other than, like we talked about when we were doing the organic chemistry, it just inserts an oxygen there. A lot more happens than just inserting an oxygen, but for our purposes, it just inserts an oxygen there to make the carboxylic acid group. The result of that is the copper goes from +2 to +1 and ends up in that orangey reddish type color that was a positive for that. So pretty much most sugars are reducing sugars in that sense, because they do cause the reduction there of like copper 2 in the Benedict's reagent. Now, the reduction of monosaccharides involves really the carbonyl group. It does produce sugar alcohols, such as D-glucose will give us this sort of sugar alcohol that is sometimes referred to, again, because it has those kind of OH groups that are happening there. Now, you're not going to probably have to do this, but really the only thing that's going to change here, right, is if we oxidize this guy, we're pretty much just going to insert our oxygen in there and take our aldehyde group into a carboxylic acid group, which is what we see here. And there it is. So that makes our carboxylic acid group on our oxidation process. By the way, just like we talked in organic chemistry in terms of the alcohol that we were just talking about, if you do the reduction, right? And that is basically some H2 happening there, H to there, right? And another H coming into there, and we will get back our alcohol. So this is pretty much identical to what we saw when you took your primary alcohol and you oxidized it to an aldehyde, and then you oxidized it one more time to a carboxylic acid, and then obviously our reduction would be heading in the opposite direction. So pretty much going from OH to aldehyde to carboxylic acid, basically. And that's what we see here, OH, aldehyde, carboxylic acid. So if you take a sugar and oxidize it, you get a carboxylic acid, you throw through reduction, you get basically a sugar alcohol that comes off of it. Any questions on that there? Let's talk a little bit about disaccharides, so a little cheese and milk to go with our bread. A disaccharide, as we talked about, is made up of 2 monosaccharides that have been put together. They basically have been put together by removing water and sticking them together, basically. Now, this slide I will star because you should know it. You do need to know the monosaccharides that make up the disaccharides. So for these different disaccharides, you do need to know the two monosaccharides that make it up. Probably going to be somewhere there on the final, I imagine. So we're going to look at each of these a little closer in just a second, but overall, maltose is a result of basically two glucose guys coming together. Lactose is a result of glucose and galactose coming together. And sucrose is a result of glucose and fructose coming together. So again, you do need to kind of know those guys. So let's take a look at each of these here. We'll start with maltose. Maltose is known as malt sugar. It's composed of two D-glucose molecules that have basically been put together again through the removal of water, basically. And it is linked by something else that you do need to know. We'll take a look at this in just a second. But it is linked through what is referred to as an alpha 1,4 glycosidic bond. And it is kind of like the name implies. It's alpha positioning on the carbon number 1 attached to carbon number 4, making a bond between those two as you remove water in this particular case. So let's take a look at that guy there. Not that, look a little bit closer. It's used in cereal, candies, and brewing. And it is found in both the alpha and beta form. And here it is. So here's our two D-glucose. They're going to come together via the carbon number 1 of 1 and the carbon number 2 there, or carbon number 4 and the other guy. What's going to happen is we're going to take water out. So however you want to think about it here, we'll go with our water. It's going to come out. The result of that is we're going to make a bond here. And this is what is referred to as the alpha 1,4 glycosidic bond. So how do you recognize that bond? Well, the way I remember it is alpha is up or down. Yeah, so when you look at this bond, it kind of looks like the oxygen is going down. Yeah, so that is like the alpha. And it's a result of this guy being obviously, not really this guy, the first guy I circled, that guy being a alpha OH group, and that's the result of it. So we'll take a look at a different bond in just a second. You'll see it's kind of shaped a little bit different. So you kind of see the bonds coming down to that oxygen between two monosaccharides. Just remember down is alpha, and that should be alpha. And the numbering is really just the numbering of the two carbons, one on each of the sugars that are making the bond. Again, that is carbon number 1. And that is carbon number 4, and that again is where it becomes the alpha 1,4 glycosidic bond. Any questions on that? This is the alpha anomer of maltose, because on the far right side here, at the other carbon number 1, we have that OH group down, and it also come in the beta version where that guy would be flipped upwards as well. Any questions on that there? By the way, if I wanted to break this up, I throw the water back in, right? And they basically just separate back out into what their original components. Now, lactose is a disaccharide that is made up of beta D-glucose and either alpha or beta D, beta D-galactose, and either alpha or beta D-glucose. Same idea here. This is carbon number 1. That is a beta OH. And again, when we come together, these guys are going to come together here and they are going to remove water. And it will form a different type of glycosidic bond. This is what is known as beta 1,4 glycosidic bond. And what happens is, as you can see, that is the bond right there. And if you look at that bond, it looks like this, like it's kind of going upwards, and beta is up, right? So that is the way you could kind of recognize it. If you see sort of a bond between these two sort of sugars kind of going upwards, that's going to be a beta. And again, the numbers here, 1 and 4 glycosidic bond. And again, that is different than when you kind of see both of them coming down to the oxygen. And what we saw previously where that is 1 and 4, and that is an alpha 1,4 glycosidic bond. So again, it does look a little bit different, and that's sort of how I personally remember it. This one kind of looks like it's going up. This one looks like it's kind of coming down to the oxygen, and again, that's the way you could kind of remember it. It's found in milk products, and people have trouble processing this one, yes, and can't have a lot of milk products and stuff like that. Now, sucrose is a little bit different of a connection, and the difference in the connection is what we see happening here. It is obtained from alpha D glucose and beta D fructose. It has a different bond as well. It actually has an alpha beta 1,2 glycosidic bond. And when we look at this, it is just drawing the outer parts there. That is carbon 1. And then we got our guy down here kind of going this way. And that is carbon number 2. And these guys are bonding this way. And that is basically the top guys coming from our alpha, bottom guys coming up, coming beta. And that is where we get both of those sort of guys in there in this case. This is alpha beta 1, 2, as carbon number 2 there on the guy on the bottom, glycosidic bond. This one has both of the symbols, alpha and beta, because they are both happening where our alpha and beta carbons are, right? That's where the connection is. If you look back at the other two that we looked at before, the connections happening over only here at like the alpha carbon. The other alpha carbon is not involved in the bond that holds them together. So that's why we don't have like two alpha or beta type things happening here. And same thing with the previous one as well. When we look at this guy, it is just between this first carbon, the other sort of alpha beta carbons way over there, not involved in the bonding that's happening. So in the case of sucrose, we also are getting the bonding happening actually at both of the sort of alpha or beta carbons. And that's why we have both alpha and beta there in the name of this glycosidic bond. Question on that? Yeah. It's carbon number 2 because the ring is different. It's only a 4 carbon ring. It's that 4 carbon ring, which means, as we talked about there, you will have, as you can see here, carbon number 1. We'll go over here, for example. That's 6, 5, 4, 3, 2. And there's our carbon number 1 that's off the ring there. And that's again why that's 2 as well. This is also why, as I talked about before, when we talked about reducing sugars, is problematic for sucrose because of where the connection's at. It doesn't have sort of that alpha or beta carbon free to kind of do the oxidation that's necessary. And that's what sort of prevents it from being a reducing sugar, as opposed to the other ones. They do have that sort of that guy open to help out with the oxidation. What's that? The top one you're talking about? Yeah, the top one, if I finish my drawing, I'll just finish my drawing up here like that. So once again, just like we did before, this would be carbon number 6. And then this would be 5, 4, 3, 2, and 1. And again, that would be like sort of like that aldose type deal where you don't have an extra carbon group off of the ring. Remember that fructose, right, is our ketone, which has, this sort of deal. And when it comes together and connects here, that carbon number 1 is left off of the ring when it makes that ring type structure. And as opposed to over here, glucose, which is an aldehyde up there. So when that guy comes in, there's nothing left off of it, and that number 1 gets sort of incorporated into the ring. Yeah. Other questions? Yeah. So you definitely need to know for each of those, sucrose, lactose, and maltose, the 2 disaccharides to make them up. And you also need to know the glycosidic bond that holds them together. Yeah, the name of it as well. You also need to be able to, if you are given a picture of that type of glycosidic bond, be able to correctly sort of identify what it is. Like it's an alpha 1,4 or something like that. Okay. So keep that in mind here. We'll take a look at this. We don't have to draw any of this, but here, if we were to hydrolyze really any of these guys, we would use water, and pretty much wherever that glycosidic bond is going to be is where they're going to break apart. And you really, in this case, would just kind of put back an H on one and an OH on the other to get us back to where we started with. So again, if we hydrolyze it there, we're going to put an H back onto that oxygen, an OH onto there, and here's both of those guys, our alpha D-glucose and our beta D-fructose. And again, because the connection is happening here, that is why we have the alpha on the top guy and the beta on the bottom guy. And again, our positioning of 1 and 2 that's happening when they get put together. All right. Good without sweeteners. All right, so for each of these, right, take a moment and what are the 2 monosaccharides that make up each of these guys? Okay, so let's take a look. Lactose is a combination of glucose and galactose. Maltose is a couple of glucoses together, right? I'll circle it twice. How's that? And then the sucrose is the one that we just saw there. A little fructose and glucose sort of action happening there. Again, for maltose, alpha 1,4. Lactose beta 1,4, right? And for sucrose, that is our alpha beta 1,2 happening there. Reconnect those. Any questions on that one there? Okay, let's talk a little bit about polysaccharides then. Polysaccharides are pretty much made up of, they are polymers, and polymers are really just long, repeatable sort of chains. So you get this repeatable unit and you just keep repeating it, repeating it, repeating it. In this case, polysaccharides are repeatable units of D-glucose. They are all basically put together by removing water and making those glycosidic bonds. They include amyloid, amylopectin, and starches made of D-glucose. Also include glycogen, which is made out of D-glucose as well, and cellulose in plants and wood, which is made out of beta D-glucose. So let's take a look at potatoes first, and it's a couple of different things here. So we have amylose here, and it is, as you can see, just maybe if I get it bigger, there we go. It is basically just a big old repeating chains here of D-glucose happening. They are put together by, again, removing water through each of those spots. And this. If we look at the bond, just like we were talking about before, they are held together by that alpha 1,4 glycosidic bond. Again, as I talked about, it kind of looks like it's going downward to that. And again, that would be carbon 1 of that guy and carbon 4 basically of that guy, making that alpha a 1,4 glycosidic bond. Now, amylose is unbranched, which means it's just a straight chain of those guys just continuously sort of repeating. Now, amylopectin, which is right next door, is also basically a big chain of glucoses together, also held together by an alpha 1,4 glycosidic bond. Once again, you can kind of see that bond just like we saw in the previous one. The difference between the two is at some point, there's going to be like a branch that's going to happen, just like in organic chemistry, things branching off of it at certain points. And at that branch point, we're going to get a different type of glycosidic bond. Once again, this is our alpha carbon right there. So that is where the alpha comes from. And the 1 is carbon number 1. This actually attaches to, not on the ring, but it attaches to that carbon 6 that's always just hanging up above the ring. And remember, that is our carbon 6 right there. And that makes an alpha 1,6 glycosidic bond. Again, basically just the location of it. This is the only guy that has an alpha or beta carbon, and that's why it's called alpha, because it's going downward. remember that the other alpha carbon or beta would be over here, and that's not where the attachment point is. Acid does that branching, it just kind of repeats back those units, and it's more branch sort of happening there. So amylose, D-glucose is held together by alpha 1,4 glycosidic bond. Amylopectin also a bunch of glucose is held together by that, but the difference is at some point you have some branching happening that you don't have in the other. So next time you look at a potato, there it is. Yes, that's what's happening there. Any questions on that? As you can see, it's 80% mainly that branch guy, kind of 20% of that straight chain. So amylose is, as we saw there, a continuous unbranched chain having that alpha 1,4 bond, while amylopectin, as we saw there and those pictures, also having those branching points. So it has two different ones, alpha 1,4 and alpha 1,6. Now, glycogen, which is, where we kind of store our energy and excess sugar, so we could use to break it back down and gluconeogenesis and use it for energy, is also a polysaccharide of D-glucose. It's similar to amylopectin, except it is super highly, I guess super is not really on there, but super highly branched. There's a lot more branching sort of happening, but basically the same deal that's happening in that amylopectin is what's happening there with glycogen, but a lot more branch points happening. Cellulose is a polysaccharide that's made up of beta 1,4 glycosidic bonds. And once again, hopefully you can kind of see the difference between alpha and beta sort of bonds. Once again, that beta kind of going upwards, if you want to think about it, and the sort of the connection point that's happening. And again, it's beta because it is coming off of, we just look at that carbon, that is our beta carbon there, which is carbon number 1 attaching over here to carbon number 4, the next guy. So beta 1,4 attachment happening here. It cannot be digested by humans, so don't eat it. Humans can't break that beta 1,4 glycosidic bond. I don't know why you would want to, but maybe. But again, it is kind of a unbranched straight chain, but going sort of upwards, if you will, because of the beta 1,4 bond. So let's take a look at each of these here. Identify the polysaccharides and the types of bonds that are happening in each of these. So let's take a look here. We have our cellulose, which we saw has the beta 1,4. Our amylose has the alpha 1,4, amylopectin, alpha 1,4 and alpha 1,6, and glycogen, the same as amylopectin, but much more branch change happening there. Any questions on that there? So that you do need to know as well. Again, the bonds there, and as I mentioned, if maybe something's given to you drawn, you need to be able to perhaps identify the type of glycosidic bond that's happening there. Any questions on that there? All right. It is. We have butter, and we'll have margarine and butter and oil as well. Yeah. If it works, maybe it does, maybe not. All right, there we go. Like, wow. All right, so let's talk a little bit about lipids. Like, does not want to move. All right. Lipids are biomolecules that contain a fatty acid or a steroid nucleus, which we will look at. They are soluble in organic solvents, but not in water. They are extracted from cells. You can use organic type of solvents to do so. There are some different types of lipids that we're going to talk about. There's waxes, there's fats and oils, which are triacylglycerols. There's glycerol phospholipids, prostaglandins, and at the end, we'll take a little look at steroids and sort of the steroid nucleus. They do not contain fatty acids, as we'll talk about. Hopefully. Maybe turn slide. There we go. Very picky. So we're pretty much gonna, in this chapter, go through all of this here, but this is actually a pretty good slide. It has a lot of the things from this chapter that you do need to know. And each of these are in some different sections throughout the slides as well. But to not ruin the ending, you do need to know sort of the components that make up these guys, the different sort of components that make it up. And so again, we'll see each of these separately down the road, but this is a nice little slide that kind of shows you what each of these things are sort of made up of. I want to move there. All right. All right, we'll just do it that way, I guess. We'll start with fatty acids. Maybe 700 clicks. Maybe. Come on, you can do it. There you go. So maybe this wasn't meant to be. I don't know. All right. So let's start with what fatty acids are. Fatty acids are long chain carboxylic acids. So just like in organic chemistry, that means it's going to have our carboxylic acid group there at the end. It typically will contain 12 to 18 carbon atoms. Because of that, as we know, they're going to be probably pretty insoluble in water because that's a pretty big carbon chain. If you remember when we talked about organic chemistry, once you hit about 5 or 6 carbons, right, solubility starts to really sort of drop off. Even though we have a fairly pretty good polar group there at the end of it, because of that long chain of those carbons, it's going to be pretty much insoluble in water. They can be saturated or unsaturated, and that means pretty much the same thing as it does in organic chemistry. If you remember, saturated meant that you have the maximum number of hydrogens for every carbon, and that pretty much means there's no double bonds, right? And unsaturated means that you do not have the maximum number of hydrogens per carbon, and that means you're going to have some double bonds happening somewhere along the chain. And then we're talking about really the sort of long carbon chain. Either it will be saturated like this. I know that's probably not about 12, but we'll pretend. Or it will be some unsaturated where somewhere along my bad mountain range here. It's getting worse as I keep drawing it, I think. Maybe why I failed organic chemistry. All right, so it's got some double bonds in there happening along the way. And the presence of those double bonds or not the double bonds actually affects sort of the properties of these fatty acids in terms of to sort of your question or about it, whether or not you'll be more like a solid sort of fat or be more of a liquid sort of fat, depending on sort of the double bonds and stuff that is happening there. Sure. All right, so let's take a look at the formulas of fatty acids. They can be pretty much like in organic chemistry. We can have a condensed sort of formula. We can also have line structure as well. Also with our condensed formula, because they oftentimes are pretty long chains, sometimes we'll use that sort of abbreviation where we have basically the CH2 unit repeated 6 times. So if you were going to be counting carbons, for example, in this particular guy, you want to make sure you don't miss all the carbons that are there. That would be 1 carbon. There would be 6 carbons there, which gives you 7. And then you would have 8 carbons there. So remember that if you have something in parentheses, that means that CH2 unit just keeps repeating. Pretty much what we got going on there. Here's just our line structure. Like normal, every one of these guys, again, just like in organic chemistry, are carbons with the appropriate number of hydrogens that should be there as well. Now, saturated fatty acids, steak. We got steak with our bread. Not good. Saturated fatty acids, they have pretty much carbon-carbon single bonds on that carbon chain. The deal with that is they're going to fit really nicely with each other. So because there's no double bonds, as you can see there on the bottom, they have the ability to really fit nice and close with each other and have some good interaction happening on the carbon part of the chain. The result of that is, by the way, they're using dispersion forces on that part of it, right? Because that's all carbons and hydrogens, but they're going to be able to interact really well with each other. They're going to sit really well with each other. And because there's a lot of good interaction that's happening, it's going to take a lot of energy to kind of break that guy apart. So they typically will have high melting points, and they're typically going to be more your solid fats at room temperature because of them sitting really nicely with one another. As you can see here, the fat on the steak there going to be very nice. And again, everything's going to line up really, really tight with one another and allowing really good interaction between the different sort of fatty acids. And again, that'll be more of a solid at room temperature. And that's different than perhaps when we see, if we do see, there we go. We'll take a look at these guys here first, though. These are some examples, some different saturated fatty acids. You can see things like coconuts, animal fat. They have, 10, 12, 14, 16, 18, 20 carbohydrates, not carbohydrates, 20 carbons. Um, and we sometimes refer to these guys as by the number of carbons they have and the number of double bonds that they may have. So, for example, if we took our stearic acid there, which is our animal fat, that would be considered an 18 to 0 fatty acid. And the 18 is basically the number of carbons, and the 0 is the number of double bonds. So sometimes people refer to these sort of fatty acids as like a 16 to 1 or an 18 to 2 or an 18 to 0 sort of fatty acid. And again, the first number is the number of carbons there are. And the second part is basically how many double bonds that there would be in each of these cases. All these guys would have pretty high melting points, as you can see. And would be more solids at room temperature, again, because each of their carbon chains are saturated and will fit really nicely with each other and create a really good interaction that's going to happen. Now, what happens when we don't have that occurring and we do have some double bonds occurring? As you can see, the presence of the double bonds pretty much kinks up the chain, and it kinks up the carbon chain part of the fatty acid. So as you can see here, not very straight and fitting nicely. We could also have, just like in organic chemistry, because of the double bond, a cis or trans type of fatty acid. And here, just like in organic, it means the same thing. Our groups are on the same side there, our hydrogens, and that's going to be cis. On the other guy, that's a trans fatty acid. And as we'll talk a little bit about trans fatty acids a little later on in this chapter, not so good in certain situations. So the problem with this is they contain at least a double bond, and instead of having that really good sort of interaction like we do in a saturated situation, we got some of guys all over the place, and there's not really good interaction between different chains of fatty acids. That they try to sit together, they're not going to sit together really nicely. That's going to allow really not great interaction between those and bonding between the different fatty acid chains. The result of that is, unlike our meat there, we're going to have more of a liquid sort of fat at room temperature because they're not going to fit nicely and be held tight together. And it's not going to take a lot to sort of break them apart as well. They typically will have a little bit lower melting points as well because of these kinks in the chain that occurs with the double bonds being present. So they're not able to pack as tightly. They have lower melting points, and these are typically going to be more your liquid fats at room temperature because of that. And again, this is really the carbon hydrogen chain on all these guys. And as you can see, is nowhere near as nice and organized. And there's lots of space between everybody. So we're not going to get really tight interaction that's going to happen. Thus, it's not going to take a lot to perhaps get those guys to kind of come apart and start to melt. And here is a table of some other unsaturated fatty acids. So we have things like butter, olives, some corn, I think this is. But we could look at these guys and also list these fatty acids based on the number of carbons and also number of double bonds. I won't do the counting, but we'll just trust their counting there. There are 16 carbons there, if you count from here all the way to our last carbon here. And there is one double bond. This would be referred to as a 16-to-1 fatty acid. Again, 16 carbons and 1 double bond. This is an 18-to-1 fatty acid. Those are what are referred to as being monounsaturated. Mono meaning one, right? One double bond happening there. And that's different than polyunsaturated fats, right? And that means it has multiple double bonds happening. So if we come to this guy right here, that is 18 carbons, and we got a couple double bonds. So that would be an 18-to-2 fatty acid. Again, 18 carbons and 2 double bonds. This would be a 20-to-1, 2, 3, 4. 20-to-4 fatty acids, got 20 carbons and 4 double bonds. Out of all these guys here, which one should have the lowest melting point? It is the guy on the bottom, right? It's got a ton of double bonds, right? So everywhere there's double bonds, that chain's going in all places, right? And we've got a bunch of those together. Nobody's going to be really near each other and held tightly. So super low melting point, -50. As opposed to this guy up here is a little better. It's got only one double bond, so it's got just a little kink in the chain. And you can see it's 0 in terms of its melting point, which is about 50 degrees better than the guy on the bottom with all those double bonds in there. So as you would move, say, this way, not that you necessarily get solid, but you'd be moving more towards a solid structure, right? Than, say, going the other way, be more of a liquid type structure. So you do need to be able to identify lipids by the number of carbons and number of double bonds, like 18-to-1, 18-to-2 sort of fatty acid. And here's another table from your book, I think, as well, that has all those guys together. And again, our 12-to-0, 18-to-3. And again, we can see definitely this guy down here with 3 double bonds, much lower melting point than up here where this guy has no double bonds happening in that case. Okay, let us continue on here and wrap this thing up, hopefully, maybe. So we've been talking about here fatty acids, and again, the presence of double bonds or no double bonds has an effect on things like melting points. So if we're looking at this sort of example, we want to assign which one should have a -17, 13, and a 69 in terms of their melting points. So clearly the one that has the most double bonds should have the lowest melting points. So I'm thinking that guy should probably end up there. Next sort of lowest melting point would be somebody with some double bonds. And clearly our saturated guy that has no double bonds should fit nicely with each other and should probably end up with the higher melting point. So again, the more sort of double bonds there are on that sort of fatty acid chain, the more kinking that's going to occur, and the less it's going to sit nicely with each other, and you're going to have less interaction between that chain, and it's going to be easier to sort of break apart in a sense. All right. So I'm glad they agree. So that's good. Just going to keep swiping. Eventually, it will change. I'll talk a little bit about prostaglandins. Prostaglandins have 20 carbons in their fatty acid chain. They have OH groups at carbon 11 and 15, and they have some trans double bond there at carbon 13. Prostaglandins happen when we have some inflammation in the body, perhaps when you hammer your thumb. Ouch, that looks painful. It's involved in sort of the inflammation process. We take some of these guys here, perhaps, if we did that, and that will prevent the formation of it, and that should hopefully prevent the inflammation and pain. Take home message: move the thumb out of the way, I suppose, when you using the hammer. So there's also fatty acids that are sometimes referred to as omega-6 and omega-3 fatty acids, and they have some good properties that sometimes are used by people. Vegetable oils are mostly omega-6 fatty acids, and what that actually means is the first double bond actually occurs at carbon number 6, which kind of makes sense. But in this case, when you're doing sort of omega-3 or omega-6, we actually start counting different than we normally have counted carbons before. Normally, right, we would start at the carboxylic acid, right, as our number 1 carbon there, because it is sort of the functional group. When we're actually doing omega-3 or omega-6 sort of counting, we actually start at the other end. So the furthest end away from that, and that would be over here, which this would be carbon 1. There are 4 carbons that are repeating right there, so that's 5, and that means right here would be carbon number 6, and that is where our first double bond is basically present. Same thing in fish oil, which is omega-3 fatty acids. Once again, we're actually going to start counting on the opposite end of where our functional group is at. That would be carbon 1, that would be carbon 2, and then here, right there, would be carbon number 3, and that would give us our omega-3 fatty acid. So if you're doing sort of omega-3, omega-6, you actually, odd as it sounds, start counting away from the carbon L-carbon, and that is where you would find it. And I know. I'm gonna keep swiping. Like I don't know how it's set, but it's like set to 32 swipes before it'll actually change slides, I think. So here we go. Here's linoleic acid, and again, starting away, starting at number 1, ending at number 6. Here, starting at 1, 2, and 3. Here's a few more. This would be a 1, 2, and 3. 4, 5, and a 6, by the way. This would be a 1, 2, and 3 in terms of our fatty acids here. So if we wanted to write fatty acids with 10 carbons, that is saturated monounsaturated omega-3 and monounsaturated omega-6, you could just start with your typical, if you want to do line structure, you can. Probably count the right number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I get that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Since this is going to be a fatty acid, I'll do my move like that there. So now I should still have 10, I hope. And saturated would mean no double bonds, right? So that would be it. It should be. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, same deal here. We'll just draw the same way. And we'll do that. We'll have our carboxylic acid group. Monounsaturated means it has 1 double bond, right? And omega-3 means we should start at this end and count. So that would be 1, 2, and 3, right? Would be our double bond happening there. And omega-6 monounsaturated will look pretty similar. And again, here we'll go 1, 2, 3, 4, 5, and 6, and lay ourselves up a double bond right there. Any questions on that there? That obviously is more of a line structure type formula. You could also do condensed structure as well, which would look pretty similar. If it comes up, obviously it looks just in condensed. Remember, in condensed formula, that is very often how the carboxylic acid group is sort of written, as opposed, and again, that represents basically that group there at the end. And again, we could see 1, 2, and 3, 1, 2, 3, 4, 5, and 6. And obviously saturated, no double bonds happening in that situation. Talk a little bit about waxes, maybe. Go. Waxes are esters of saturated fatty acids and long chain alcohols. Back here. Ester is that a move there? Yes, a little carbon to oxygen to carbon type move is happening. So we have our fatty acids, which basically has the carboxylic acid group, and we have an alcohol, which basically has that group. And then we know we're basically just going to take out a little bit of water, right? And that's going to give us our ester connection here, right? So just like in organic chemistry, we'll take out the water, slip the two together there, and it will make that ester bond. And that's what we see here. This is beeswax here, and there's our ester bond happening in that one, carnauba wax there, and some other wax as well. And same idea, we would break that apart pretty much where they come together. And to the right, like we talked about with esters, is the alcohol part, right? Just like we sort of named those guys in organic chemistry. Going towards the double bond is the carboxylic acid part, which would come from our fatty acid part in this case. And so it's basically pretty similar to the ester bond esterification reaction that we saw in organic chemistry, where we take a long chain alcohol and this long fatty acids. Obviously, there's a lot of non-polarness happening on both ends of this guy. This is a long chain of carbons and hydrogens, which is nonpolar. That's a long chain of carbons and hydrogens, which is nonpolar, which is why wax is kind of nonpolar, right? And doesn't mix really well with water and stuff like that. So it creates sort of a coating, and why water tends to bead on things that have been waxed, like your car, right? It kind of beads on it because it doesn't mix with it, right? And if you have a really waxed car. Fats and oils, we're going to talk about now, are also called triacylglycerols or TAG sometimes. They are esters of glycerol and is produced just like we just talked about the esterification reaction. So we're going to take out water and basically squeeze them together. They're formed when the hydroxyl group on glycerol basically reacts with the carboxyl group of our fatty acids. So triacylglycerol, which is one of the things you do need to know, and you pretty much need to know that, and you need to know that as well. So you do need to know what glycerol looks like, and it's a 3-carbon unit that has basically OH groups on it. And basically, we take our fatty acids and we make our ester bonds here through our esterification reaction by removing water. So a triacylglycerol is made up of a glycerol unit and 3 fatty acid units, and they're held together by an ester bond in this particular case. And once again, like we talked about, we're basically just going to remove water from the situation. In this case, we would remove 3 waters to put them together. Here we have saturated fatty acids, which is also going to be helpful in terms of it being more of a solid type of fatty acids that's happening. Olive oil contains a high percentage of this monounsaturated fatty acid. And as you can see here, same ester bond happening with glycerol. But we have those double bonds there, which again are providing some kinking to that chain. We're not going to get some good interaction here. More liquid sort of triacylglycerol there, as we see in olive oil. We don't need to know the names of them, so don't worry about it. Melting points of these guys, triacylglycerol, that is a fat, typically will be a solid at room temperature. And that's prevalent what we see in meat, milk, butter, and cheese. Again, that's going to be the guys on the fatty acid chain part, pretty much are saturated. No kind of double bonds happening there. We have a triacylglycerol is going to be more of an oil. That's going to be more of a liquid at room temperature. Again, because of those double bonds that it contains. So it's really the fatty acid part here in the triacylglycerol that's going to give it the property of either being more of a solid or more of a liquid at room temperature. Oils that have more unsaturated fats, they can have cis double bonds that cause these kinks. And again, they cannot pack as tightly, just like we were talking about previously, and that will give us those lower melting points than we see with more of those saturated fats, as we can see in our picture here. So let's talk a little bit about some of the properties here. Bless you. Because we pretty much have that ester bond in these triacylglycerols, you pretty much can do similar type of reactions that we talked about previously. We could do a hydrogenation reaction. And a hydrogenation reaction is when we take our double bonds and turn them into single bonds, right? So it's really the same reaction that we talked about in organic chemistry, where we add a couple of hydrogens, double bond becomes a single bond. Here, where this is going to happen is on the fatty acid part of it, where we have our double bonds, and we'll try to turn some of these things into single bonds. Why would we want to do that? As I turn these double bonds into single bonds, what happens to the property of my fat? It becomes more, actually becomes more solid, right? So if I get rid of some of the double bonds, it's going to sit nicer, hence margarine. Yes, our little middle factor between oil and solid butter, right? Kind of hard, but not solid, right? A little still soft. And again, that is made by doing some hydrogenation of fats, where we do this reaction and it turns some of these double bonds into single bonds. You perhaps heard the words partially hydrogenated. Yes, that's what that means. They basically add some hydrogen and turn some of those double bonds into single bonds. The result of that is that fatty acid chain is going to sit a little bit better with each other. It's going to raise the melting point, and it's going to go from a more sort of liquid sort of fat to more of a solid type of fat. And again, that's how we get things like margarine, for example. Hydrolysis is where we're going to basically split the triacylglycerol back into its components. And just like we made the ester bonds by taking the water out, if we wanted to break those guys back apart, we would put the water back in, and that's the hydrolysis part of it. And obviously that happens at the bond. So as I mentioned before, hydrogenation converts some of those double bonds into single bonds, increases the melting points, and that is how we kind of produce things like margarine and shortening, which are more solid fats, but still not super solid, right? Like on a piece of steak or something like that. And here is the hydrogenation reaction. Frankly, it's the same idea. I got one double bond, two double bonds, three double bonds. So I need 3 hydrogen molecules, one for each double bond. That's going to then turn this part of our triacylglycerol into a more saturated. It's going to allow these guys to interact a lot better with each other. And again, that's going to give it a more sort of solid state than the liquid state by doing that. It's got a weird setting on this one. What are the products of these things? Who cares? Because we don't. So cis and trans fatty acids, as we talked about here, cis is with bulky groups on the same side, just like we do in organic chemistry. So this would be our cis fatty acid, and our trans would be on opposite sides of the double bond. And depending on what type of fatty acid that you had, some are not so good as others. So it's been found over the years that trans fatty acids are not so great for you. They are formed during the hydrogenation of cis double bonds that converts some of those into trans double bonds. In the body, it does behave like a saturated fatty acid. This is sort of an old slide, so I'm not sure exactly how much, but there was a big movement a long time ago, not too long ago, to sort of remove trans fatty acids from a lot of things and that type of stuff. And the reason they did that is a lot of studies reported that it raised your LDL cholesterol. LDL is good or bad? Bad, right? L for lousy, right? H for heavenly, right? That's a good way to remember that, by the way. Take it with you. It's free. Yeah, your HDL is your good cholesterol, and it'll lower your good cholesterol, raise your bad cholesterol. So that's not such a good thing. So a number of years ago, a lot of people, there was a lot of states and stuff that sort of everybody kind of moved away from trans fatty acids and kind of using that. All right, so there are more unsaturated fats in vegetable oil. True or false? What do we think here? It is true, right? So unsaturated means we have double bonds, which means we will have a lot more kinking and more liquid type of thing there. Vegetable oils have higher melting points than fats. That is false, right? And that's because fats have saturated, right? And they sit really tight and they should have a higher melting point. Hydrogenation will convert cis to trans. That is true. And animal fats have more saturated fats. That is true as well. Again, saturated meaning those chains are going to sit really nice and going to be more solid. Here's our hydrolysis reaction. And just like before, we're going to basically break it right there at our ester bond, just like in organic chemistry. To the left is really our alcohol. So to get our alcohol back, we just need a hydrogen there. And on the right, in this case, is our carboxylic acid, which needs each of those guys need the OH. That's all going to be supplied by the water, which is our HOH, basically, right? So that's going to go back to get our glycerol unit, and those OHs will get back our fatty acid units. Talk a little bit about the saponification of soap. And that is a reaction with a strong base. It splits a triacylglycerol into salts of fatty acids, and you could do this by using a strong base. You could use something like potassium hydroxide, which gives you a softer soap because potassium's involved. What makes hard water and hard stuff like that is things with large positive charges. Yeah. That's why people have water softeners, for example, in their house, right? To exchange the higher charge positive ions for things like sodium, right? Or potassium, if you can't have too much sodium, which has a +1 charge and that softens water and stuff like that. So soap is basically made here, and I think we touched a little bit upon it when we were talking about esters as well. But when you do that, it is going to break us apart here. We will get our glycerol back, but here we will get essentially soap. And as we talked about, soap is really this long chain sort of fatty acid that has that carboxylic acid type group at the front part of it. Remember, in terms of soap, there's two parts. There is that polar head is sometimes referred to, and there is the non-polar tail of soap. And as we talked about, I think, remember that dirt is mostly non-polar. So that works really well with the back part here of soap. It's able to basically surround our dirt with that part of it. And it's going to mix really well, like dissolves like. So non-polar is going to work really well together. That would put our polar part of soap out there in front, as we talked about. And obviously, when we go to use soap on something, we typically wash it off with water. And because the polar side of soap aligns itself on the outside, when you wash it now with water, the water will mix with the soap and will take the trapped dirt out with it. And that is how soap works again. These are good things to know, perhaps. I don't know. All right. What are the products? Who cares again? I feel like I had that question a second ago. Keep swiping until things stop. Here's our hydrogenation. Not that you don't need to draw any of this, but the idea here is what we talked about. Each of those hydrogens are pretty much just going to turn those guys into single bonds, and everything else will pretty much be the same. You just add a couple of hydrogens, one to each of the carbons that are there. Maybe. So find that setting somewhere. I couldn't find it. All right, let's then talk about glycerol phospholipids. You also need to kind of know the components of these guys. These are the most abundant lipid in cell membranes. They're composed of a glycerol unit, two fatty acids, a phosphate, and an amino alcohol. Say like choline is an amino alcohol. So this guy is made up of our glycerol unit, which is that 3-carbon unit, two fatty acids, phosphate group, and an amino alcohol. And that is pretty much what makes it up here. This also means that it has a couple of different sort of properties based on what it is. These are some of the amino alcohols, like choline is an amino alcohol. And it will have some polar amino groups. And because it has this amino alcohol on it, this type of phospholipid actually has sort of a non-polar part and also a polar part as well. The polar part being where the amino alcohol is, the non-polar part being where the fatty acid part of this phospholipid is, which is what we see here. So our fatty acid part here, which is the non-polar tail of this guy, and the polar head is our amino alcohol. And that gives, again, really, this sort of lipid works really well with cells, right? as you have things that are polar coming through, right? And you have things that are non-polar. So again, it gives us some interaction that it can work with both things. Again, the non-polar part will work well with anything that kind of flows through that is non-polar, and things that are polar will work well with the polar head part of it. So these are, again, our sort of four components: two fatty acids, a glycerol, a phosphate group, and again, an amino alcohol over here. Now, sphingolipids is also something that you should know. They are similar to phospholipids. They contain sphingosine, a long chain amino alcohol, a fatty acid, a phosphate group, and a small amino alcohol. So you do need to know the components of this guy. Again, a fatty acid, sphingosine, phosphate group, and an amino alcohol. They have, again, kind of the same idea: non-polar region, polar region here. So the polar head being where the amino alcohol is, the non-polar part again being the fatty acid. Um, here's an example of one, I think. There's sphingosine, which is similar to glycerol, except it does have a nitrogen group in there. And again, our fatty acid sort of long chain happening there. So this is an example of one of these guys. Here again is our sphingosine. There's our fatty acid, which would be our non-polar part. That would be our polar part, which is our amino alcohol. And again, it still has the phosphate group that sort of binds both of these guys together. This guy, for example, is found in nerve cells, and it has an amide bond. And we remember our amide bond, right? Our nitrogen right there, our carbon oxygen to our nitrogen, right? From like an amine and a carboxylic acid coming together. Now, the steroid nucleus is this guy. It consists of three cyclohexane rings and a cyclopentane ring. It has no fatty acid. You need to be able to recognize this as the steroid nucleus. You don't need to draw it, but you need to be able to recognize it as a steroid nucleus.
Are you pointing to
The whole thing, yeah. That whole thing is the steroid nucleus, and if you see it, you need to be able to recognize it. One of the most common ones is, speaking of cholesterol, cholesterol has a steroid nucleus right there, and that's the most abundant steroid in the body, as we talked about a second ago. Hopefully, mostly HDL, right? Not so much LDL happening. And again, it's got some methyl groups, an alkali chain, and some OHs basically happening. So you do need to be able to recognize, again, like I said, the steroid nucleus, not necessarily draw it, but if you see it, you need to be able to recognize it. All right. So out of this chapter, like I kind of mentioned, I think I probably mentioned in the video as well, you need to know the components of those different sort of phospholipids. You need to be able to identify a fatty acid by a number of carbons and double bonds. You know a little bit about, again, some of the properties: more double bonds, right? Lower melting points, right? And more liquid, less